In lesson 37, J.J. Thomson made the discovery that atoms are made up of, they're essentially a big blob of positive material with little electrons, little negative particles called electrons. In this lesson, we have Robert Millikan comes along and he wants to know what is the charge of a single electron. This is in 1909, and this is a monumental task in 1909 to find out what the charge of a single electron is. We know it's 1.6 times 10 to the negative 19 coulombs, which is a ridiculously small number. But in 1909, Millikan said he could do it, and he came up with yet another ingenious physics experiment to find out what the charge of a single electron is. It's called the oil drop experiment. And you can read all the notes here. Let's just look at the diagram. So what do we have here? We have a positively charged plate. We have a negatively charged plate. So any electrons that find their way into this drum, it's all going to be in a container here. Any electrons that find themselves are going to be repelled from the negative plate. So there's going to be electrostatic force pushing them up. And there's going to be a gravitational force pulling them down. And just like in J.J. Thomson's experiments, where you balanced the magnetic force with the, which one's that going to go? Where you balance the magnetic force and the electrostatic force, now we're balancing two other forces. We're balancing the gravitational force with the electrostatic force. So what Millikan did was that he took some mineral oil in the bottle and he sprayed it through the bottle. And when you spray it through this bottle, there's all kinds of friction, and that friction will cause these oil droplets to become charged. Now, they may become charged with one excess electron, or they may lose electrons, or it may be 10 billion electrons. Who knows? But every droplet that comes out of here will have a different, will be charged. And therefore, if it's positively charged, well, then it's just going to go in here and it's going to go, it's going to, gravity and the electrostatic force will pull it down. For the negatively charged ones, what will they do? They will be repelled from this plate. Gravity will pull them down, and if you can adjust the electrostatic force enough, what can you make happen? You can make these oil drops actually be suspended here. If the electrostatic force equals the gravitational force in this setup, and you have negatively charged oil droplets, then some of them will actually suspend. Some of them will be, if they have a lot of excess electrons, then yeah, they're going to be just pulled back up to this one here, or they won't even make it down here. But some will suspend, and once they're suspended, then you can measure certain things about them, like their mass and their, not their mass, their density and volume and such. So let's see how his experiment works. We've got the electrostatic force equaling the gravitational force. And we know from the previous unit, or from the previous lesson, that the electrostatic force is EQ, the electric field strength times the charge. We know from a long time ago that the gravitational force is mass times gravity. And therefore, we can come up with this formula. To calculate the charge of the electrons. All right, and what they needed here was, when you've got the M here, the M represents the mass of the oil droplet, not the mass of the electron, the mass of the oil droplet, which was a difficult one to measure. Electric field strength, easy to measure. Gravity, we know, is 9.81. So the mass of the oil drop was a difficult one to measure, but he got it, and he did this experiment millions of times, or not millions, but tons of times, and he eventually came up with a value. Now, there's a permutation of this formula. We know that E can also be expressed as V over D, E equals V over D, electric field strength equals voltage divided by distance between the plates. And so we can, just over here, we can write V over D times Q equals mg, and therefore when you're solving Q, you get this, mg d over Q. So there's another permutation. If in the question they give you the voltage and the distance between the plates, then you can use this formula. If they just give you the electric field strength, you can use this formula, or you can just use this formula and then change that when you see fit. Either way, so then let's go on to describe how measuring the mass of the oil drop. It says it was a tough one. So often they would only, these oil droplets, they wouldn't be suspended there indefinitely. They would just hang there for a couple of seconds and then they would be splattered onto one of the plates. And so Millikan made these little hash lines right here. And then he would see, and he knew the distance between the hash lines, and then he would be able to measure the diameter of these oil drops, and then from the density of the material, he could calculate the mass. Okay, and then he said he did it thousands of times. He did it, and he found out. So remember that the oil drops may have one excess electron, or 2 or 10 or 1,000,000 or whatever, but what he found out was that all the answers he got were all multiples of this number. He had never got anything lower than that. So therefore, he assumed that the ones with only one excess electron, the charge of that electron would be 1.6 times 10 to the negative 19. So if it had 2 excess electrons, it would be 3.2, and so on. Okay, and then you should go to YouTube and you should watch a whole bunch of videos on Millikan's oil drop experiment. They're very cool, and it's a cool experiment. And here's your example. An oil drop in the Millikan apparatus has a mass of 3.3. It's observed to float between the parallel plates. So if it's floating, then the electrostatic force will be gravitational force, right? And then you're just going to go through this whole manipulation, or you've just memorized the formula. And in this question, they give you the distance between the plates and the voltage. So we're going to change that. Solve for Q. Plug in your numbers. Make sure you change the centimeters to meters. Everything else is straightforward, and you get not 5.7. That's the answer to the whole question. 9.0 times 10 to the negative 19. .0 times 10 to the negative 19 coulombs. So that's how much charge there was on this oil drop. And if we want to figure out how many excess electrons it has, we're just going to divide that by 1.6, because we know the charge of one electron is 1.6 times 10 to the negative 19. And you end up getting 5.7, but we know you can't have 0.7 of electrons, so we're just going to round that up to 6. So this has approximately, or not approximately, it has 6 excess electrons. And we're talking about small numbers. So when you say the mass is 3.3 times 10 to the negative 15, right, you're dealing with a whole lot of uncertainty in that number. So that's why you're getting 5.7 and not exactly 6. All right, and that is the end of Millikan's oil drop experiment. So now we know that atoms are made up of positive material and electrons, and now we know that the charge of thanks to Millikan, the charge of a single electron is 1.6 times 10 to the negative 19 coulombs. See you for lesson 39, Rutherford.